Two pieces of advice before we begin, and they're up here. The first piece of advice is do hard problems. Now, hopefully, when we say hard, we don't mean impossible, and we don't mean things that require lots of arithmetic and algebra. By this point, we really hope you're good at arithmetic and algebra, so we're going to go on faith that you can do that. When we say hard, we want to make problems that have you think. That's what we mean by hard. So if you look at a problem, you're like, I'm not sure I could do this, that's a good problem to look at. So that's what we mean by do hard problems. And the second piece of advice is to take care of your health, which means, get plenty of rest, plan your week appropriately. You don't have to be a non-stop study machine for the next 4 days. You can break your study up into reasonable amounts of time and still do fine. Don't pull all-night study sessions. We've had students show up for exams and fall asleep. It's not a good strategy. It usually doesn't work very well. It's better to, keep to your schedule, get enough sleep, eat good food, go out and take walks. And if your body is doing well, you'll be able to think better. And of course, a better score, what we all want. We want to get all the points. So with those two pieces of advice, here we go. 17 problems to go. Find the value d so that the plane 2x plus y plus 3z equals d will perpendicularly intersect the curve r of t is 2t squared plus 8t plus 1, comma 8t minus 7, and t to the fourth minus 8t plus 1. So, what do we have? There's a couple of keywords. They even highlighted this keyword, perpendicularly, which of course we can also think of, it's going to intersect at a right angle. And so what are we after? Well, we need to find this value here. So there's this plane sitting here, and we have to think about this for a moment. We have a curve, and we want the curve to intersect this plane. Now, curves intersect planes all the time. That's not hard. But oftentimes what happens is that when a curve intersects, it does so at a very not right angle. What we want is we want to get it so that it intersects at a right angle. So in other words, we go straight into the curve, straight into the plane and cross through. So to figure this out, what we need to think about is how do we intersect? Well, to do that, we look at the derivative. Now the derivative tells us motion. So it's a pretty good idea that if we see a curve, there's probably going to be a derivative involved at some point. It is calculus after all. We should be doing calculus-like things. So here's our derivative. And what's going to happen here is that our derivative tells us how are we behaving at any point in time. Now we want to behave where we perpendicularly intersect. Now for a plane, if I want to be perpendicular to a plane, we key off of these coefficients, namely 2, 1, and 3. That's our normal vector. So here's our idea. If I want to be perpendicular to our plane, we need to have our direction match our normal vector. Well, now we have to be a little bit careful, of course, when we say match. When we talk about match, we mean is parallel to. So, what do we need? We need to have 4t plus 8, 8, and 4t cubed minus 8 to be in the same direction as this normal vector, so it's submultiple. We'll call it S of 2, 1, and 3. So that's what we need to have happen. So this gives us a series of equations. 4t plus 8 has to be twice S. That's from the x-coordinate. 8 has to be equal to S. It's from the y-coordinate. And 4t cubed minus 8 has to equal 3 times S. Well, the good news is the middle one, easy to solve. So we now know that S should be 8. So this tells us that we need 4t plus 8 to equal 16. And of course we need 4 times t cubed minus 8 to equal 24, because I'm plugging in S equals 8. It's probably easier to solve the first one here. 4t plus 8 equals 16. That says 4t has got to equal 8. which says that t has got to equal 2. And we'll double check. If t equals 2, 4 times 2 cubed, that's 4 times 8, that's 32 minus 8 is 24. So that also checks out. So we now have a time. We're like, woohoo, we found it. Well, no. What we found is our time. So this says at time t equals 2, the direction of the motion is going to be the same as the normal vector to the plane. So what do we need? Well, we need to make sure that the plane is going to hit the curve at time 2. So when I say hit the curve, the original curve, not the derivative. So where is the curve at time 2? So at time 2, where are we at? We plug in 2 into our curve, and we get 2 times 2 squared, which is 8, plus 2 times 8, 16, plus 1. And then we get 2 times 8, 16, minus 7. 2 to the 4th, that's 16, minus 8 times 2, which is 16, and 1. Plus 1. And 8 plus 16 plus 1, that's 25. 16 minus 7, that's 9. 16 minus 16 plus 1 is 1. So that says that's the point. So here, this is the point we want on the plane, because this is where the curve will pass through that has the right normal. And we want to make sure that the plane hits that at the right time. So we're almost done. Now that we have our point, plug it in. So we have that d should be equal to 2 times 25 plus 9 plus 3 times 1. So that's 50 plus 9 plus 3, giving us 62. And there's our answer. So this is a question about motion, and there'll be several questions about motion. And oftentimes, it pays to stop and think, what is it we're really looking for? How can we find it? What should be things which are parallel? What should be things which are perpendicular? And if you can think about those kinds of relationships, these problems usually aren't so bad. Find the second order Taylor polynomial of f of xy equals e to the power 3x cosine 2y at the point 0, 0. So Taylor polynomials, and this is a second order Taylor polynomial. What does that mean? Well, what it means is there's lots of derivatives. In general, if you want a Taylor polynomial, here's our generic formula. F of a comma b, so it's the value of the function. Then you go to the first derivatives. So f sub x evaluated at ab times x minus a plus f sub y evaluated at ab times y minus b. And then you go to the second derivatives. So fxx evaluated at ab over 2 factorial x minus a squared plus fxy at ab times x minus a y minus b, and then plus fyy at ab over 2 factorial y minus b squared. It's a long equation, barely fits on the page. And even then, you have to squeeze it there at the end. But essentially, what's the idea? When we're talking about Taylor polynomials, we want things to match. So we want to have all our derivatives matching up through the end. So really, when you see this type of question, it's all about taking derivatives. Lots and lots of derivatives. And then we're going to do evaluation. And then we're going to plug it all together and get our answer. So we start with our function. So here's our function. E to the 3x cosine of 2y. So we take our first order derivatives, f sub x, that would be 3 e to the 3x cosine of 2y. And f sub y would be minus 2 e to the 3x sine of 2y. So taking derivative with respect to x and then taking derivative with respect to y. And we have to go and take our second order derivatives, all of them. So 9 e to the 3x cosine of 2y. So when I talk about fxx, you start with the first derivative with respect to x and take the derivative with respect to x again. So that's why it's 3 times 3 giving 9. fxy, well, here you actually have two choices. come up to the derivative with respect to x, take that derivative with respect to y, or go to the derivative with respect to y and take that derivative with respect to x. You'll get the same answer either way. It's just a matter of taste. Which one do you prefer to do? So you'll get minus 6 e to the 3x sine of 2y. And then we have f y y. So go here to our derivative with respect to y, take that derivative again. So here we'll end up with minus 4 e to the 3x cosine 2y. All right, so the first step, take all your derivatives. The next step is you have to evaluate. You'll see that in our equation here, these aren't the functions. So don't take these functions and plug them into the different pieces. That's not how it works. What you need to do is you need to plug in numbers into those. And numbers come from evaluation. And this is where you have to pay attention to where's the evaluation at. Where's your polynomial centered? It's at 0, 0. So that's good news for us because 0 is a good friend. It's easy to evaluate things that involve 0. E to the 0, cosine 0, well, both of those are 1. Fx at 0, 0, we get 3 times e to the 0 times cosine of 0, which will give us 3. Fy at 0, 0, that'll be minus 2 times e to the 0 times sine of 0, which sine of 0 makes the whole thing 0. Fxx at 0, 0, that'll be 9 times e to the 0, which is 1, times cosine of 0, which is 1. So that gives us 9. Fxy at 0, 0, well, that'll be minus 6 times e to the 0, which is 1, times sine of 0, which is 0. And fyy, minus 4 times e to the 0 times cosine of 0. So that's minus 4 times 1 times 1. That gives us minus 4. All right, so we took our derivatives. We evaluated all our derivatives, and the last thing to do is to plug them in. So that's why it's good to know the formula. So we can say that our Taylor polynomial, oops, I should have said this is approximately. So our Taylor polynomial is the value of the function, which is 1, f sub x, which is 3, times x minus, in our case, 0, so 3x, f sub y, which is 0 times y, but that'll be 0, fxx, which is 9, divided by 2 factorial, well, that's 9 halves, and then it's going to be x minus 0 squared, fxy, which will be 0, so that term will go away, and fyy, that's negative 4, divided by 2 factorial, that makes it minus 2 times y squared. And that's our second order Taylor polynomial. So for these problems, if you see second order Taylor polynomial, it's really, once you know the formula, it's really not bad. It just says, take your derivatives, evaluate, and put them all together. Boom, you got your answer. Life is good. All right. Well, that's good. We're doing pretty well so far. Let C be the closed curve in the plane that starts at 6, 0, then goes to 6, 6, then goes to negative 2, negative 2, then goes to negative 2, 0, and finally returns to 6, 0. Now there's a hint before we even start about what kind of problem this is. Because we see this expression, closed curve in the plane. And when you see that, well, we're in the plane, we're a closed curve. That says Green's theorem. So we're thinking Green's theorem before we even start this problem. All right, well, what do we have? We have a closed curve, and we can actually sketch this. We start here at 6, 0. Then we go to 6, 6, which we'll say is up here. And then where do we go? To negative 2, negative 2. So that's down here. So here's negative 2, negative 2. And then we go to negative 2, 0. So that's right there. And finally we return to 6, 0, which is right there. And what's our goal? Well, our goal is to find the integral along this curve of e to the y minus y dx plus x e to the y plus arctangent of y plus pi dy. Now, of course, we know Green's theorem says we're not going to do that integral. We're going to do a different integral. So we're going to think about what integral we're going to do. So let's think about what's going to happen here. Well, for the moment, let's see what Green's theorem would say. Green's theorem would say this is the integral over our region of what? Okay, so let's just pause and say, if we think of this as m dx plus n dy, the Green's theorem says that the integral over the curve of m dx plus n dy is equal to the integral over our region of n sub x minus m sub y dA. So we're going to take the second piece, this second term, take rid of that with respect to x. So we have an x times e to the y. That'll be e to the y. And the arctangent goes away because there's no x inside of that arctangent, so that's gone. Okay, so there's my n sub x. And now I'm going to subtract from this n sub x the derivative of the first term with respect to y. And that derivative is e to the y minus 1 dA. Well, good news. E to the y's cancel. Minus minus makes plus. So this becomes the integral over our region dA. Now we're like, woohoo, easy problem. But maybe there's a subtlety. If you look at the curve, there's something going on with this curve that we haven't quite seen. So we have to think about how to deal with this. So what haven't we seen before? Well, this curve is a closed curve, but it crosses through itself. So how are we going to handle that? And the answer is, we're going to think of this as in two parts. So we have one part here, which we'll just think of this as our first triangle. So in other words, we're really thinking of, let's break our line integral, our curve, up into two pieces. So in our first piece, this will be what we have. And we're going to do the following. We look at it and we say, what's our orientation? Well, it's oriented so that if we were standing on the curve and walking along it, our region would be to our left-hand side. So this is a good orientation. So in this case, what we have is that the integral will match the area. So what's the area? It's a triangle. Its base and height are both 6. So we'll get 1/2, 6 times 6, or 18. Now, on the other hand, we have a second part. This part down here. So we are thinking about splitting it up into two parts. And now, if we look at this little part, again, we'll think of it separately, and we say, what's the orientation? Well, now we are going in this direction, which means it's clockwise. That's the wrong way. So what happens if you're going the wrong way? You flip the sign. Orientation just says if your orientation is off, change your sign. So here, when we go through and actually do the part, we're not going to get area. We want minus the area because the orientation is off. So we want minus 1/2, and then it's a triangle with base, width, height 2. So we get minus 2. So our answer is now we just put these two together. So it's going to be 18 plus negative 2. Final answer, 16. So pay attention to orientation. And another philosophy, if you need to, think about how to break things up and say, well, it's hard to do it all at once. Break things into smaller, manageable problems. In fact, it's a good way to solve problems. If you can't solve the whole thing, can you solve a part? Okay. How about the other part that's left? And work your way through it. Find the tangent plane to z, which is written as a function of f of xy, which is x cubed plus 2xy plus y squared plus 3 sine y minus 1 plus 6 e to the x minus 1 at xy equals 1, 1. So this is one of our find the tangent planes. It's a very straightforward problem. No big surprises. It's just good to know what we mean by a tangent plane. In this case, what is a tangent plane? You can think of it in terms of Taylor polynomials. It's your first order Taylor polynomial. So it's the value of the function plus f of x at ab times x minus a plus f sub y at ab times y minus b. So if you need a tangent plane, there's a couple of ways to do it, and this is one. We'll see another way, another type of problem later on. But when you have your tangent plane, you have z as a function of x and y, then there's the way that we usually handle that is to use our formula. So we're going to need to take some derivatives. So our original function, that's x cubed plus 2xy plus y squared plus 3 sine y minus 1 plus 6 e to the x minus 1. So we take the derivative with respect to x. 3x squared plus 2y. There's no x in there, plus 6 e to the x minus 1. F sub y, well, there's no y in the first term. The second term, that'll become 2x. Then we'll get 2y. And then derivative of 3 sine y minus 1 will be 3 cosine y minus 1, since the derivative of sine is cosine. And the last term has no x. We only need to go through our first order derivatives because this is a tangent plane. We now plug in at our point of tangency, which is at 1, 1. So what happens when we plug 1, 1 in? We're going to get 1 plus 2 plus 1 plus 3 times sine of 0. Well, sine of 0 is 0, plus 6 e to the 0, which is 6. 1 plus 2 plus 1 plus 6 makes 10. F sub x at 1, 1. Well, that'll be 3 plus 2 plus, again, 6 e to the 0, which is 6. That's 3 plus 2 plus 6. That's 11. And f sub y at 1, 1. That's 2 plus 2 plus 3 times cosine of 0. Well, that's cosine of 0 is 1. So that's 3, giving us 7. So what do we have as our final answer? Well, we take the value of the function, which is 10, plus we take the value of the derivative at the point, so that's 11 times x minus 1, and then plus the value of the function at our point, which is 7, times y minus 1. And there you go. We weren't asked to simplify, but really, it's pretty much as simple as you can hope for. And there's reasons to leave it in that form, depending upon what you'd want to do with it later on. All right. Well, let's do an easy problem. Enough of these hard problems. All right. Find the integral 0 to square root of a half, integral y squared to 1 minus y squared of 24xy minus 24y cubed over 1 plus the quantity x plus y squared, all cubed, dx dy, by using the change of variables. U equals x minus y squared and v equals x plus y squared. And there's the region below. Now, notice here, it's telling us to use the change of variables. That's very suggestive about how we should start this problem. We should probably start by doing the change of variables. Now you might say, but I don't want to do change of variables to solve this integral. Well, too bad. Follow the instructions. Because if you don't follow the instructions, we don't have to give you credit. Follow the instructions. If it says do something, do it. All right, so in this case, we're going to do our change of variables. But to be honest with you, I don't think I'd really want to try to integrate that function as it's written currently. All right, so when we're doing a change of variable problems, we're going to have the variables given to us. So that's the easy part, and we don't have to stress about finding those variables. So u equals x minus y squared, v equals x plus y squared. From here, there are sort of three things to do. So when you see a change of variables, after you do that, I recommend doing it in the following order. Do your Jacobian. Then, after you do your Jacobian, work on the function. And then after you work on your function, work on your bounds. So I like to go in that order. And so let's talk about what that means. So when we're talking about the Jacobian, I'm talking about looking for the Jacobian of x, y. So we're going to do a little 2 by 2 derivative. And derivatives here are very forgiving. So if you don't remember the exact form, it's okay. The key is you have, say, your variables u and v in one direction and x and y in the other direction. So if we have u sub x, 1, and u sub y, minus 2y, v sub x, 1, v sub y, It's 2y. Take your 2 by 2 determinant. 2y minus minus 2y gives us 4y. Now, if by any chance it's negative, throw the negative out. You always want your Jacobian to be positive. So, what does that tell us? Well, what that tells us here is that 4y dx dy is going to become du dv. Now, this order doesn't matter. It could be 4y dy dx. It could be dv du. We're going to figure out the right order later on once we get our bounds set up. But the key here is to look at our function. So let's, that we're integrating. So looking at this, I really want to get a 4y attached to dx dy. And looking at the numerator, I see, aha, they both have y's and multiples of 4. So I'm going to pull a 4y out. In fact, I can pull out a 24y. So this is 24y times x minus y squared over 1 plus x plus y squared cubed. So that's our current function. But remember, we want to pull off a 4y. So I'm going to really think of this as 6 times x minus y squared over 1 plus x plus y squared cubed times 4y. And this part will go with the dx dy to become part of our du dv. We don't need to worry about that. So what do we need to worry about? Well, we need to worry about this part. So here the key is now, how do we express these terms in terms of our new variables u and v? And most of the time it'll be pretty clear. You just look for expressions like x minus y squared or x plus y squared. And here we say, aha, there's an x minus y squared. And actually there's an x plus y squared. So this is going to become 6u over 1 plus v cubed. So there's our function. All right, so we have our function, and we have our Jacobian. Now we have to worry about our bounds. Okay, so how do we handle the bounds? Well, think of your current bounds, and you only need to write down the bounds that are actually bounding the region. So for instance, you might say, well, what about this bound right here? This is y equals square root of half. Well, see, y equals square root of half is this line. I don't need to worry about it because it's really just a single point. That's not a bounding curve. I'm looking for the bounding curves. In this case, there's 3 bounding curves, so those are the ones I'm going to focus on. And I want to figure out what happens to them. So we have y equals 0, x equals y squared, and x equals 1 minus y squared. Again, what are we doing? We want to take these expressions and see what they become in terms of u and v. Now, some of these are pretty straightforward. For instance, this x equals y squared becomes x minus y squared equals 0, which becomes u equals 0. And similarly, this x equals 1 minus y squared becomes x plus y squared equals 1, which becomes v equals 1. So those two are not so bad. Now the last one shouldn't be too bad either. We see that y equals 0. Now, there's not a single term with y. They both have y. But this tells us that what? U has to equal x, and v has to equal x, because I'm plugging in y equals 0 into both these expressions. So they both equal x, which means they both equal each other. So in terms of the uv plane, those are going to be our 3 bounding curves. So we come to our uv plane. U and v. We have u equals 0, which is a straight line, u equals 0. We have v equals 1, which is also a straight line. And then we have u equals v. And we're looking for the region which has all 3 of these curves on the side. Well, we can spot it. It's a triangle. It's right there, that triangle. So, all right, so that's good. We're ready to piece everything together now. So now that we've figured out our Jacobian, our function, and our region, we're ready to say that the integral becomes what? Well, the function will become 6u over 1 plus v cubed. That's our function. The 4y dx dy becomes du dv. And now we have to face a choice. We say, okay, do we want to integrate first with respect to u, then with respect to v, or would we rather integrate first with respect to v and then with respect to u? In other words, what order should go here? The answer is, which integral would you rather do? Now looking at this, I say I can integrate 6u all day long. But 1 over 1 plus v cubed, no. I don't want to do that. So let's do the integral we can actually do pretty easily first. So let's pick that as our order, du dv. So now that we know our order, we can say, okay, what are the bounds? Well, where does v go from? We go from 0 up to 1. So 0 to 1. Where does u go from? Well, what's happening is I've picked a v, and I'm going to go between these two curves. So I'm going to go from u equals 0 to u equals v. So that's the two curves I'm going between. So 0 to v. All right. So now, are we done? No, because we were told to find. See, if we said find, you actually have to carry it all the way to the end. So we start by integrating. So we're integrating first with respect to u. And, well, we chose it so it wouldn't be so bad to integrate with respect to u. So that would be 3u squared over 1 plus v cubed. Evaluate from u equals 0 to u equals v dv. And you plug in 0, you get 0, which is nice. You plug in v, what do you get? Well, you get 3v squared over 1 plus v cubed. We're like, ooh, well, that's rather nice. Somebody cares about us, and they want us to get an answer. All right, well, why? Well, normally if I just had the 1 plus v cubed, that would be tough. But the 3v squared upstairs is a good sign. So I can make a substitution. So, for instance, I could say, I've already used u, so we're going to keep going down the alphabet. Here's our next letter, w. If I set that to 1 plus v cubed, then dw is 3v squared. Which means that if we carried out this substitution, this would become dw over w. Now we have to update the bounds. When you plug in v equals 0, you get w equals 1. Plug in v equals 1, you'll get w equals 2. So this becomes log of w from 1 to 2, which is log of 2 minus log of 1. But log of 1 is 0, so our final answer is log of 2. All right. So, all right. Well, how do you recognize these problems? Well, they're pretty easy to recognize because you're doing an integration and they'll say, change the variables. Here's your new variables. So, in some sense, recognizing them is not the hard part. It's just a matter of the process. And there's not really any single part of the process which is bad. Just be careful, work through the steps, do the Jacobian, pick out what you need for that, do your function, get your bounds, and work it out. So, okay. Let C equal sine of t, t cosine t, and half t squared, where t runs between 0 and 2 pi. Find the integral along C of e to the x dx plus dy plus x plus 2z dz. Now, looking at this, you might say, this looks like a conservative line integral type problem because you have some crazy curve and you have some function. But there's two reasons why this is not a conservative line integral type problem. The first reason is because those types of questions aren't on the exam. That's a good reason. But the second reason is this is not a conservative function. You can check because you'll see here there's an x which says if it were conservative, there should be a term called xz in the potential, which means you'd have to have a z over here in that dx term, but there's not one there. So this is not a conservative integral. So how do you do these integrals? And the answer is you go back to your definitions. So what do we mean? Well, so if you're doing the integral along a curve of e to the x dx plus dy plus x plus 2z dz, go back to the definition says you're going to do everything in terms of time. You're going to stick with the curve that was given. So in our case, we're going to have 0 to 2 pi. And now we're going to go through this expression. Everywhere we see an x, we put sine t. Everywhere you see a y, we're going to put t cosine t. Everywhere where there's a z, we put a half t squared. Now when we see the d's, that means the derivative of those functions. So we'll have e to the sine of t times the derivative of sine t, which is cosine t. That's the first piece, e to the x dx, plus dy. Well, take the derivative of this function, so that would be product rule, cosine of t plus t times minus sine of t. All right, and now go to the next part. Plus x, well, that's sine of t, plus 2 times z, which is going to be t squared, and then dz, well, the derivative of z, that would be the derivative of a half t squared is t. So we're translating all the pieces into the correct thing. So everywhere you see an x, put what the x should be, where is y, put what y should be, so forth and so on. And now you have an integral with respect to t. Now the thing is just do it. Once you have it set up, it's just a matter of doing it. But if they're nice, you'll have something happen. So for instance, you'll see here there's a minus t sine t. When you distribute this in, you'll have a plus t sine t, which means you actually get a little bit of cancellation. So your life gets a little bit simpler. So what do we end up with? So we're going to end up with 0 to 2 pi, e to the sine t, cosine t, plus cosine t, plus t cubed, dt. And at this point, it's really just calc 1. Now you'll notice this integral looks bad, but then you say, oh, wait a second, derivative of sine is cosine, and so if you do a substitution, this has an antiderivative e to the sine t. Now you might say, whoa, that was really nice. Almost too nice. Well, it actually had to happen. Because what do you have? You have e to the x times the derivative of x. This was perfectly set up for a chain rule. All right. Then the integral of cosine is sine. And then the integral of t cubed is 1/4 t to the 4th. And we're going to evaluate from 0 to 2 pi. So e to the sine of 2 pi, that's e to the 0, which is 1, plus sine of 2 pi, which is 0, plus 1/4 times 2 pi to the 4th. Subtract e to the 0, which is 1, sine of 0, still 0, and 1/4 times 0 to the 4th is 0. Well, the 1's cancel. The good news is this 0 also cancels with that 0, leaving with 1 0 left over, but that turns out to be 0. And so, what are we left with? Well, we have 1/4 times 2 to the 4th, which is 16. So that leaves us with 4, and we also have pi to the 4th. So 4 pi to the 4th power. All right. So that's how we can do a line integral if it's presented to us in the form something dx, something dy, something dz. Just put everything in terms of t. Use the method of Lagrange multipliers to find the maximum and minimum possible values in the corresponding locations where they are achieved for the function f of xy equals 2x plus 3y, given that x squared plus xy plus y squared equals 84. Now looking at this problem, we might say, well, what technique should we use? Let me ask you, what technique should we use? Yeah, we should use Lagrange multipliers. What's the key? It tells us to. All right. Now, even if it didn't tell us that we had to do Lagrange multipliers, we could figure it out. Because we have a function we're trying to optimize and a constraint that's given to us. Now, occasionally in Lagrange multiplier problems, it is possible to be like, I have a more clever way to do it. I can avoid using Lagrange multipliers. However, let's be explicit here. If a problem says use Lagrange multipliers, you better use them or you won't get the credit. And we want to get all the points. That's our goal. Got to get them all. So how does the Lagrange multiplier problem work? Well, we identify what we want. This is what we're trying to optimize. Then we have our constraint. So we call that g of xy. And we really want to make sure we have a constraint equal to a number. If there's variables on both sides of your constraint, push everything to one side. Because you want to have just your function g of xy equals a number. And now what we do is we set up a series of equations. So f sub x is lambda g sub x, and f sub y is lambda g sub y. So working this out, we'll get, in our case, f sub x root of 2x is 2, is equal to some multiple lambda g sub x. So that would be 2x plus y. And then we get f sub y, which is 3, is some multiple of g sub y. Well, that's x plus 2y. All right. Well, now we have to solve this. I should say there is a third equation, namely our equation for our constraint. But let's start with the first two. And the goal for the first two equations is to find some relationship between x and y. And how do you do it? Well, here's my philosophy. When in doubt, solve for lambda. And I'm a person who's full of doubt. So I always solve for lambda. All right. So what do I mean by that? So in the first equation, we'll get that lambda is 2 over 2x plus y. While in the second equation, we'll get that lambda is 3 over x plus 2y. But of course, lambda is lambda, which means that these two expressions have to equal each other. We can now cross multiply. And what do you get? Well, you'll get 2x plus 4y is equal to 6x plus 3y. And clean that up, move stuff around. We can subtract 3y, we can subtract 2x. We'll get that y should equal 4x. Now, this is a new constraint. From our equations, f sub x equals lambda gx and fy equals lambda gy, we have a new relationship. Come back to your original constraint. So originally it was x squared plus xy plus y squared equals 84. Now we're going to substitute y equals 4x. So everywhere where I see a y, I'm going to put a 4x. So x squared plus x times 4x plus 4x quantity squared equals 84. And you'll notice that something beautiful has happened here. It really has become x squared. And then there's one of those. Here it's 4x squared. And here you have 16x squared. So x squared times 1 plus 4 plus 16. That equals 84. Now 1 plus 4 plus 16 is 21. So 21x squared equals 84. So that tells us that x squared has better be equal to 4, which leads us to two possibilities, namely x equals 2 or x equals negative 2. Now when x equals 2, y is 4 times 2, which means we have a point, 2 comma 8. And when x equals negative 2, y is 4 times that, which means we have the point negative 2, negative 8. So these are the 2 points that come out. Whatever happens has to happen at these 2 points. So let's find out what the function is. So if we plug 2, 8 into our function, so f at 2, 8, that would be 2 times 2 plus 3 times 8. So I'm plugging into our original function. That's 4 plus 24, which gives us 28. If we plug in negative 2, negative 8, we're going to get something very similar. In fact, the only thing that changes is now everything has a negative sign. So what will come out is we're going to have negative 28 at the end. So this 0.28, this is going to be the max value of 28. And this point here is going to have a min value of negative 28. Now, look at the problem. Not every problem says, give us the point. Sometimes it just says, give us the value. Sometimes we're just after the point. Make sure you know what the question is asking. Also, think about the question. It might be you're trying to optimize something, say, for a problem where you're building something, where it doesn't make sense. You can't have negative height. And that can help you also eliminate possibilities. All right. Find the line which is contained in the plane x plus y minus 3z equals 7 and perpendicularly intersects the line 3 plus 5t, 2 minus 4t, and negative 2 plus t. So this is from a recent final exam. But you might say, wait, this sounds really familiar. This sounds a lot like a quiz problem. Because it is a lot like a quiz problem. In that it's a quiz problem where the numbers have been slightly changed and a few of the words have been moved around. Other than that, It's the same ideas. See, the quiz problems have great ideas. And if you find yourself like, I've run out of problems, there's a lot of quiz problems left. Just go dig. All right. Now, how do we do this? We have to think about what's happening geometrically. We know we're after a line, so our final answer better be a line. We know it's contained in the plane, and that it perpendicularly intersects the line. So what do we have? Well, think of the picture. We have here a plane, and now that's our plane x plus y minus 3z equals 7. Then there's this line which comes through space and hits this plane. So this line here, this is not in our plane currently. It's a line coming through our plane. And what are we after? Well, we're after a line which is in our plane, which somehow stays in our plane, but also is perpendicular to that line there. Okay, so that's our picture. Now, you might say, is that picture accurate? Well, in a sense, yes, but really what we're going for is just to understand things. A good picture is one that helps you understand, not necessarily one that's accurate. So we start by thinking, okay, we need a line. So whenever you're asked to find a line, what do you think? Well, there needs to be a point, and there needs to be a direction. So we say, okay, what's the point? Well, the point will be an intersection. See, this point where our original line intersects our plane. So if we think of our original line, we have our x, y, and z. We plug those in. So we'll intersect the plane when x, 3 plus 5t, plus y, which is 2 minus 4t, minus 3 times z, minus 2 plus t, is equal to 7. So we start grouping. That's 5t minus 4t minus 3t, which would be what? That's negative 2t. 3 plus 2 plus 6, that'd be 5, that'd be plus 11, equals 7. And so what does t need to be? Well, that becomes 2t equals 4, which means t equals 2. Now that's the time. At time t equals 2, that's where the line will intersect our plane. So we plug t back in. So plug in t equals 2. We'll get 13, comma, 2 minus 8, it's negative 6, comma, and negative 2 plus 0, sorry, negative 2 plus 2, which is 0. So 13 minus 6, comma 0. And to double check, you can just say, does x plus y minus 3z equal 7? Yeah, it does. Okay, so this is our point. So now we have our point. 13, negative 6, 0. What about our direction? So oftentimes, if you're asked to find a direction of something, we start by saying, well, is there something perpendicular to it? And in this case, we can say, yeah, there's actually two things it's perpendicular to. It's got to be perpendicular to our original line. So we know that our direction has to be perpendicular to our original line, which has 5, negative 4, 1 as the direction of that line. But it also has to be in the plane, which means that if we come to the plane and look at the normal vector to the plane, that the line has to be perpendicular to that. So what's that? Well, that's 1, 1, negative 3. And once you know that you're perpendicular to two different things, you're great to go. Well, why? Well, to find something perpendicular to two different things, you cross them together. So we're going to take 5, negative 4, 1, cross 1, 1, negative 3. So we set our equations up, I, j, k, 5, negative 4, 1, 1, 1, negative 3. What we get? I, negative 4, negative 3, that's 12. I, j times 1, that's j. K times 5 times 1, that's 5k. Then we have 1 minus 4 times k, so that's minus 4k, but I'm going in the wrong direction, so I have to subtract. J5, negative 3, that's minus 15j. But then I have minus minus, so that makes plus. I, 1, 1, that's plus I, but I went the wrong way, so that's minus I. So that says 11, 16, 9. Now I feel like, oh, did I go too quick? I should check. So it's always think about, can I check my computation? Or is there a way to verify? Now with cross products, it's super easy. Just take the dot. 11 plus 16, that's 27, minus 27, 0. Perfect. 55, all right, minus 64 plus 9. That also equals 0. Perfect. All right. So we now have the direction. It's 11, 16, and 9. Once you have your point direction, you can now write down your answer. There's two ways to write things down. You can write things in vector format, or you can write things in parametric form. I prefer parametric. Oftentimes we'll accept either. So unless we specify, do it in whatever you feel comfortable in. So in our case, let's see, we'll have x equals, y equals, z equals. I start with the point, so it's 13, negative 6, 0, and then do the direction. Plus 11 times t, plus 16 times t, and plus 9 times t. And there's our line. We found it. Right there. All right. Let S be the solid cube, 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1, and 0 less than or equal to z less than or equal to 1. Find the flux through the boundary of S for some crazy-looking vector-valued function. All right. Well, what kind of problem is this? Let's test. What kind of problem do we have? It's the divergence theorem. What are some clues that we're doing our divergence theorem? The word solid is a big clue. Also flux through a boundary. That's another clue. So what do we have? Well, we're trying to compute the flux through the boundary of our cube. Now, this is a pretty easy shape to draw because cubes are not, that's not the best looking cube, but that's a cube. It's not too hard to draw. So we're looking for the integral through the boundary of our surface of f dot n. So when we talk about flux, flux is the integral of f dot n. So that's what we're after. According to divergence theorem, so this is the divergence theorem type question. If I can spell divergence theorem. Okay, well, I'll say that's the correct spelling. All right, according to the divergence theorem, this is the integral over our solid of the divergence of f dv. Now, let's see, what does this become? Well, that's the integral over our solid, and let's do our divergence. So you come to the first term and say, what's the derivative of the first term with respect to x? So the first piece here, there's no x at all. So that's completely gone. In the second piece, we have just a single x, and so we're going to end up with z cosine of yz. Now go to the second part. So our second term, take the derivative of that with respect to y. There's actually just a single y, and so we're going to end up with everything that's attached to it. X secant of xz tangent of xz. Plus, go to the third term, yz e to the xy, taking the derivative with respect to z. And again, there's actually only one z term, so you get y e to the xy. In general, remember how does the divergence work? You take the derivative of the first term with respect to x, add the derivative of the second term with respect to y, and the derivative of the third term with respect to z. Okay, so that's it. Well, no. What we've done is we've transformed the problem from a two-dimensional integral on 6 different faces, because the cube has 6 faces, into a 3-dimensional integral of a function. So now we have to think about how we want to integrate these. Now here's sort of an observation to make. Suppose we wanted to integrate z cosine of yz. There's no x, so really we have to say, okay, which would be better to integrate first? Integrate first with respect to z or with respect to y? If you integrated with respect to z first, you'd have to do some sort of a product rule. Well, not the product rule, the integration by parts, which is where the derivative becomes... all right, anyways, you have to do integration by parts. So probably you want to integrate first with respect to y before you integrate with respect to z. Now, if you come here, you can ask yourself the same question. I only have x and z. And well, which one would we want to integrate with respect to first? Well, probably integrate first with respect to z. Because if we integrate first with respect to x, we're going to end up with integration by parts. And here it says, well, what do you want to do here? Now this involves x and y. And here we'd want to integrate first with respect to x. So now we come up with a quandary. Well, which one do we integrate with respect to first? Because each one of these says we want to have a different thing go first. How do we solve our quandary? Well, the answer is to notice we have these beautiful things called plus signs. So what we can do is we can really split this into 3 parts. And on each part, we'll just go in the right order. That makes that part easy to work with. All right. So let's do our integrals. So integral, integral, integral. Everything's always 0 to 1 because it's a nice cube. The only thing that we have to decide is the right order. Z cosine of yz. And here we said what? It's better to integrate with respect to y first. So we'll go dy, dz, dx. Plus integral 0 to 1, integral 0 to 1, integral 0 to 1, x secant of xz, tangent of xz. And what's best? Well, integrate with respect to z first. And then we'll do x, and then we'll do y. And finally, 0 to 1, 0 to 1, 0 to 1. And here, well, it's best to integrate with respect to x first. So we'll do dx, dy, dz. Whoop, almost ran out of space. All right. So when you integrate with respect to y, well, here you're going to get something nice. If we integrate with respect to y, you're going to get in the first layer here sine of yz, evaluated from y equals 0 to y equals 1, because that's a really nice integral to work with. Essentially what's happening is, remember you're treating your z like a constant. So that z that came out in front came because of the chain rule. And so when you plug this in, what does this become? Well, this becomes integral 0 to 1, integral 0 to 1 of sine of z dz dx. Now let's come here. X secant of xz plus tangent of xz dz. If we integrate that with respect to z, well, the x acts like a constant. Essentially, we have a secant tangent. What's something that's the antiderivative of secant tangent? Secant. So what's happening here is that this becomes secant of xz evaluated from z equals 0 to z equals 1. So what we end up with is integral 0 to 1, integral 0 to 1 of secant of x minus 1. Because we have to plug in z equals 0, secant of 0 is 1. And then we have dx dy. Now in our last piece, well, the integral of y e to the xy with respect to x, well, that's going to turn out just to be e to the xy, again evaluated from 0 to 1. And that'll leave us with, and this is x equals 0 to x equals 1, which is e to the y minus 1 dy dz. All right, so we did each one individually, and now we're in pretty good shape. What's the integral of sine? Negative cosine. And we're going to evaluate from 0 to 1. So this becomes integral 0 to 1 of minus cosine of 1 plus 1, because I'm going to subtract cosine of 0. So minus minus cosine 0. Okay, dx plus, okay, do we know the integral of secant? Yeah, you got it. Good. So this is natural log secant x plus tangent x. And of course, we also have minus x. And we're going to evaluate from 0 to 1. And when we evaluate that, well, when you plug in 1, you'll get log of secant of 1 plus tangent of 1, which is just some crazy number, minus 1. And when you plug in 0, you'll get 0, which is nice. Integrate that dy. And then the last part, that's an easy integral. This is e to the y minus y. Evaluate that from 0 to 1, which becomes e minus 1 when you plug in y equals 1. Subtract e to the 0 minus 0, which is actually another 1. and that's going to be dz. And the last integrals are actually super easy because they're just now constants that are being integrated. So we have at the end, when we integrate this, minus cosine of 1 plus 1 plus log of secant of 1 plus tangent of 1 minus 1 plus e minus 1 minus 1. And if we wanted to, we could sort of merge things together. So we have a minus cosine of 1 from this part, a log secant of 1 plus tangent of 1 from the second part, an e, and then we have plus 1, minus 2 more, minus 2. And there we go. Done. Done. Easy, right? Easy. Well, it's not too bad. I mean, you look at it and you're like, okay, what do? You do your divergence. You apply the theorem. Then say, let's break things into parts. Let's be smart. What's the right way to do the integration to make the integration easy? And just work through it. Be careful. And you'll be okay. Let h be the part of the sphere, x squared plus y squared plus z squared minus 2z equals 1, where z is greater than or equal to 0. And let f equal negative y comma x comma e to the x cubed plus y cubed. Evaluate the surface integral, integral of h of del cross f, also known as the curl, dot n, where n are the normal vectors to the sphere which point towards the center. Now, before we start, what kind of problem does this look like? Stokes theorem. Yeah. What gives away that we have a Stokes theorem question? There's a couple of clues. Yeah, the fact that you see a curl involved. And the other thing that happens is if you think about the surface, and you probably think, well, it would have helped if they gave us a picture. This was back in the days before we got good at drawing pictures. Nowadays, we're much better. We would probably give you a picture. So what does this picture look like? What is this? It's a sphere. Now, we only care about the part where z is greater than or equal to 0. So let's start with what z equals 0 looks like. In the xy plane, which is where you have the sort of the bottom part, you have the circle x squared plus y squared equals 1. So you have this circle right here, x squared plus y squared equals 1. And then you have a sphere that's above it. So it comes up and does that. So I know that's not a very well-drawn sphere, but imagine I could draw a sphere. The accuracy of the picture is not important. The ideas are important. Okay, so there's our surface. This is our surface H. Now, what's happening? We also know something else about this surface, in that we're told about the normal vectors. This is essentially giving us an orientation. So when we have a Stokes theorem question, there's always an orientation aspect. Now in this case, it says that the directions point towards the center. So when I'm on my surface, I'm pointing towards the center of the sphere. All right, so our goal here is to compute this surface integral, curl dot f. Now, Stokes theorem says you have three options. Option number 1 is do the integral that you're given. Almost always, we never go with option 1, because that's never the easy way. Option number 2 says, I can do the following. I can turn this into a line integral on the boundary of h of f dot t ds. So in other words, I can say, what's the right boundary? What's that bounding curve? Get an orientation, make sure I get a parameterization which matches that orientation, and then I do a line integral. That's usually not too bad. And in this case, it's about as much work as what we're going to go with. And you're saying, well, which one are you going to go with? I prefer the third option, which is to say, look, they gave us a surface, but we can pick a better one. What's the key? Pick the surface which has the same boundary, but is simple. Now, if you look at what we have here, what we have is our boundary is what's happening in the xy plane, because we start at z equals 0. So our bounding curve here, this is the edge of the unit circle. That's what our bounding curve is. So now we ask ourselves the question, what would be a better surface that has the same boundary? Well, just make it flat. Make it disk. So in some sense, what you can think of happening here is we have this sphere here, and we're just going to deflate it. We're just going to... It's like we're slowly letting the air out of a balloon until it becomes nice and flat. Now, why do we like things which are flat? Well, they're much easier to work with because the normal vectors become very simple. That's why we like things which are flat. They also have much simpler descriptions, generally speaking. Now, you have to think about the orientation. Now, here's how I like to think about the orientation. So, currently, we have an orientation where we're pointed inward. So when I deflate, the orientation comes along. So if I'm pointing inward and I let the air out, I'm going to end up pointing down. So the orientation which will be consistent as we follow it down, as we deflate, will be straight down. So here our orientation is 0, 0, negative 1. In other words, this is our new normal vector to our new surface. I'll call this surface G. So we can say, aha, this is the same as the integral on the new surface of G of del cross f dot n. Okay, so let's go ahead and carry this out. Let's see what we get. So we need to do del cross f. So that's I, j, k, del, that's our partial derivative, so partial partial x, partial partial y, partial partial z, and then our f, minus y, and x, and e to the x cubed plus y cubed. Now, we could do the whole thing, but I see there's a lot of problems we still have yet to do. So I'm going to make a note that this is something, something, and here we know these don't matter. So I'm making a note. You could actually compute these, and but why don't they matter? Because of the normal. Because we're going to end up dyeing this with our normal vector, which is 0, 0, minus 1. Now note that previously they mattered. Those terms mattered, but once we've made it flat, that 0 knocks stuff out. So I really just care about the k. So if you compute the k, what do you end up with? Well, partial x, which is 1, and then minus partial y of negative y, so minus 1. So it becomes something, something 2. All right, well, now we're ready to go. Because what do we have? We can say it's the integral on g, and then our del cross f, it's something, something 2, dot 0, 0, negative 1, dsa. Well, that becomes negative 2. And that's a constant. I can pull it out. So that's negative 2 times the integral of dsa. Now, if you just integrate dsa, that's area. So we get negative 2 times our area of our surface. And that surface is this surface here. It's the one that we're using. Well, that's the surface is a circle. It's a circle of radius 1. So that has area pi. So negative 2 pi. And there's the answer. Now, you might say, do we have to do it this way? And the answer is no. And let me just sort of hint at what you would do if you were going to go with this option here. Okay, so if you're going to go with that option, the key is to say, what's your boundary? Well, the boundary is the unit circle, but because of the orientation, it's the unit circle going backwards. And so you have to be careful because it means you're going in the opposite direction from where you normally go. So you have to get a parameterization that works for a circle going backwards. And here's one that does it. Cosine of t, negative sine t, comma 0. So this is where time goes between 0 and 2 pi. So that's a parameterization that goes backwards on your boundary. And the reason I'm saying backwards is, again, it matches with the orientation that you're given on the surface. So if you now integrate on your boundary of h f dot t ds, well, what you'll discover is you integrate 0 to 2 pi, and what does f become? Well, you'll get minus y, which will become sine t, comma x, which is cosine t, comma stuff, which is messy, dot. Now you have to do the t. So for t, you have to make sure what happens. Well, this is minus sine t, comma minus cosine t, comma 0. You have to make sure this has length 1. It turns out this has length 1. You just take the magnitude. So you're good to go. And then you have to say, okay, well, what is ds? Well, you have to take the magnitude again, and it turns out dt. If you multiply this out, this becomes negative 1. So you get the integral of 0 to 2 pi of negative 1 dt, which is negative 2 pi. Which means that either way you do it, you'll get the right answer. So if you're much more comfortable doing a line integral, do it. I like doing the surface integral because it really, for me, I like to think of, let me change the problem. I don't like the problem you gave me. I want to do my own problem. It's more fun. All right. Find the integral along the curve. Ooh, more line integrals. 2 plus yz to the negative 1/2 ds, where c is 1/3 t cubed plus 2 times t minus 1 e to the t and e to the 2t. All right. Now here, this is really a line integral. We really have to do it. So what is ds? ds is the square root of x prime squared plus y prime squared plus z prime squared dt. So this is sort of the other line integrals. You have two kinds of line integrals. One kind is the one we did a while back, integral of like m dx plus n dy plus p dz. Those are fun. This kind is the integral of something ds. And then you have to go through and work through, well, what is your ds? What does everything become? So in our case, let's see what we get. So we take the derivative with respect to t, and then so we get, in the first entry, we'll get t squared squared. Then we take the derivative of the second entry with respect to y. Now, product rule. So this would be 2 e to the t plus 2t minus 1 e to the t. And, we actually get cancellation. And so what this becomes, when you take the derivative of the second term, it just becomes 2t e to the t. So 2t e to the t squared. That's the derivative with respect to y. Then your last term would be 2 e to the 2t squared. Okay, so there's our ds. Well, we got to clean that up, because that looks like that'd be hard to work with. But maybe it's not so bad. Notice something here. You should always be suspicious that if you have something in the square root, one of two things should happen. That either they were very nice and they made sure we'll factor that. In other words, it's something that can be squared, or there's something waiting out in front. I'm suspicious that it's the first one, because right now it looks terrible. And but hopefully it factors. So I like the t squared squared, and I like the 2e to the 2t squared. These look like nice square terms. And if you think about what you have in the middle, what do you have? Well, this is really, pausing for a second, 4t squared e to the 2t. And you'll notice, like, ooh, e to the 2t, that matches, and t squared matches. In fact, you can write it as 2 times t squared times 2e to the 2t. So you'll see the 4 got broke up, but that's because I wanted something that matched with the 2e to the 2t. In other words, you have a squared plus 2ab plus b squared. So this becomes the square root of t squared plus 2e to the 2t quantity squared, or simply t squared plus 2e to the 2t. All right, so that's our ds. Good. So how do we find our integral? Well, the integral becomes the following. We take our original expression, and after we found the ds, now we put everything in terms of t. So we go from our bounds, 0 to 1, and everything gets rewritten. So the 2 is just 2. The y, well, that's 2 t minus 1 e to the t. And then z to the minus a half. Well, take e to the 2t to the minus 1/2 power, and that's e to the minus t. And then your ds becomes t squared plus 2e to the 2t in dt. The e to the t, e to the minus t cancel. You have a plus 2. Notice you also have a minus 2, so those will cancel. So what do we have? This becomes the integral 0 to 1 of 2t times t squared, so that's 2t cubed, plus 2t times 2e to the 2t, so 4t e to the 2t. So this is not so bad. That's not so bad. Now, in the interest of time, we'll sort of make it a little bit short here. The first integral, that's 1/2 t to the 4th, and then in the second integral, what would we have? Well, you'd end up with 2t squared e to the 2t. No, you wouldn't. No, you wouldn't. You would end up with 2t. Sorry, I'm trying to do integration by parts in my head. I'm getting too old for this. 2t e to the 2t, and then we're going to subtract e to the 2t. Is that right? Well, when in doubt, just take the derivative. So if I keep the first term, take the derivative of the second term, that gives us 4t e to the 2t. Then we'd have a 2e to the 2t, but we also subtract 2e to the 2t. So yeah, that's right. You can do the integration by parts. It works out. Now you plug in 0 and 1. So if we plug in 1, you get 1/2. Plus, here you get 2 e to the 2. Then you're going to subtract e to the 2. So, yep. And then minus, plug in 0, you get 0 plus 0 minus 1. And so we end up with e squared, and then plus 1/2 plus 1 means we get 3/2 plus e squared. All right, good. So let g of xy equal 7 plus x plus 3y squared plus 4xy plus 6x cubed plus xy squared minus 5x squared y be the third order Taylor polynomial to f of xy centered at 2, 1. Now, what does this mean? Let's be careful here. Third order, that just tells us how many derivatives we match. So when we say third order, that says all the derivatives match up through order 3. So the first order derivatives, the second order derivatives, and the third order derivatives. All right, and it's centered at 2, 1. And we're asked to use this to determine all the second order derivatives for f of xy at 2, 1. So how can we do this? Well, here's the key. The way this is set up is that the first, second, and third order derivatives for g match the first, second, and third order derivatives for f. That's what it means to be a third order Taylor polynomial. So if I want to find fxx at 2, 1, which is where I'm centered, it's going to match what gxx at 2, 1 is. If I want to find what fxy at 2, 1 is, it's going to match g of xy at 2, 1. And if I wanted to find what f sub yy at 2, 1 is, that's got to match g of yy at 2, 1. In other words, the Taylor polynomial will match the function up to wherever that your cutoff is. In this case, it's up to the third, so we're definitely going to match in the second. So really, once you have that one little nugget of understanding, this problem becomes, oh, let's just take a look at what happens to the derivatives of g. And then we figure it out. So let's look at what happens to the derivative of g. We need to find g sub x. So we go through. That'll be 0 plus 1 plus 0 plus 4y plus 18x squared plus y squared minus 10xy. And we'll need also g sub y. So 0, 0, 6y, 4x, 0, 2xy, and minus 5x squared. All right, so that's what we get when we take our first order derivatives. And now we take our second order derivatives. And we had to take our first order derivatives to get our second order derivatives, so gxx. So we come to gx, and we just read off and say what happens when I take derivative with respect to x. Well, 0, 0, 36x, 0, and minus 10y. Gxy, well, we're going to get 0 plus 4 plus 0 plus 2y and minus 10x. Now, one thing you can do to check is go to your derivative with respect to y and now take the derivative with respect to x. You'll see you get 0, and then 4, and then 2y, and minus 10x. They should match. Gyy, well, this becomes 6. That 4x goes away, plus 2x, and the minus 5x squared goes away. All right, so here are our second order derivatives with respect to x. And now, to finish it, we evaluate. So gxx at 2, 1 would be 36 times 2 minus 10 times 1. That's 72 minus 10, which is 62. Gxy at 2, 1, that would be 4 plus 2 times y, which is 2, minus 10 times 2, which is 20. So that's 6 subtract 20 is negative 14. And gyy at 2, 1 would be 6 plus 2 times 2, 6 plus 2x, which would be 10. And these are our answers that we're after, 62, negative 14, and 10. So if you're after some information about the partial derivatives and you have the Taylor polynomial, just remember the Taylor polynomial has to match. Find the tangent plane to the surface xy squared plus e to the power x minus z plus sine of y plus 2z equals 5 at the point 1, negative 2, 1. All right. What an interesting surface they've given to us. So here we have this crazy expression. And it's a surface in three-dimensional space. And we want to find the tangent plane. Now, the good news is if you need a plane, you need to have a point. Okay, that's good news. We have our point. But the other thing is we need to have our normal vector. So if you're in the situation where you have f of x, y, z equal to some constant c, then to find your normal vector, this is where you use your gradient. So gradient of f at x, y, z at our point gives the normal. That's the key here. Now you might say, well, what happens if I don't have this form, f of x, y, z equals c? Maybe I have like crazy stuff on the left and crazy stuff on the right. And the answer is, put everything on one side. Now you have everything equal to 0. Perfect. Perfect. So I guess the moral is, if you have crazy stuff and you're asked to find a tangent plane, throw everything to one side, take the gradient, life is good. So we have a plan. And so recall, our plan is we're going to think of this here as a function f of x, y, z. Recall, where did this come from? This is really a level surface. So we're finding something perpendicular to a level surface. Okay, so this is our chance to flex our gradient muscles. So gradient of f, now that's a vector, which is a collection of partial derivatives. So we go through and take derivative with respect to x. First one will be y squared. Then we'll have e to the x minus z. And there's no x in the last part, so we're done with that. Take derivative with respect to y, 2xy. No y in the second term. And the last term, sine of y plus 2z, the derivative of that is cosine of y plus 2z, comma. Go to our last term, derivative with respect to z. No z in the first. Here, derivative with respect to z, you're going to have a minus, and the minus is going to come from the chain rule, because there's going to be minus in front. And then the second one will be plus 2, cosine y plus 2z. Again, the 2 comes from the chain rule. Okay, so there's our gradient. Now the next thing to do is to evaluate. So we're going to take our gradient and plug in 1, negative 2, 1. See, this is not a normal vector yet. What it is, it's a function. A normal vector has to have numbers. So don't say, aha, I found my normal vector, and your normal vector, or rather we should say that your tangent plane should look like planes. You shouldn't have lots of crazy functions in there. All right, so we plug in 1 minus 2, 1. So let's see, y squared, that'll be 4, then plus e to the 1 minus 1, that's e to the 0, which is 1. Then we have 2 times x times y, that's minus 4, plus cosine of minus 2 plus 2, it's cosine of 0, that's 1. And here we have e to the 1 minus 1, that's 0. There's a minus in front, minus 1. Plus 2 cosine of y plus 2z, that's cosine of 0, so that's plus 2. Or, if you like, that's going to be 5, comma, negative 3, comma, 1. So there's our normal. This is our normal. And now we can write down the equation of our plane. So the normal gives us our coefficients, 5x minus 3y plus z equals something. So how do you find the something? Use the point now. So the something has to be 5 times 1 minus 3 times negative 2 plus 1, or 5 plus 6 plus 1, which is 12. So that's 12. And that's our answer. We're good. All right. I like that problem. I hope we get that problem on the test. Evaluate the integral over the curve of f dot dr. It's an oriented square loop in the xz plane centered at the origin with side length 2. And they even gave us a picture here. And our function, f of xyz, is, it's something. Okay. So what kind of problem do we have here? Well, there's a couple kind of problems. One kind of problem is just do the integral. Now, if we just want to do the integral, we would break our curve up into 4 pieces and do 4 line integrals. And none of them are particularly bad, but there's 4 parts. We'd have to parameterize, we'd have to work through them all. Doesn't sound fun. But what's another way to view this problem? Stokes. Okay, so what's the clue that you have Stokes? Well, the clue is you have a closed curve in space. So if you have a closed curve in space, in 3-dimensional space, that works great for Stokes theorem. So what you can do is you say, aha, this closed curve, this is the boundary of some surface. Now, they just didn't give us a surface. So what we get to do is we say, well, what surface do we want to put in? Now, this is your chance to be not creative. In other words, be as easy and simple as possible because we like ourselves, so we want it to be easy. So what's a nice surface which has this boundary? Well, we just put in a flat square. Boom, there's our surface. Life is good. Now, the other thing we have to decide, though, is what's the right orientation for this surface. In other words, which side is the top? Now, you might say that doesn't make sense because it's standing vertically. But we always talk about surfaces. There's a top side and a bottom side. So, in other words, should we be heading in the positive y direction or the negative y direction? Well, which one is the right one? Imagine you stand, just pick a side. So suppose I come here, and here I am standing, and I walk along the curve. Is it oriented in the correct way? And if the answer is yes, then I'm standing on the right positive, or I'm standing on the top side. In this case, if you walk along it, you'll see that the region is to the left-hand side. So that is the right orientation. So the right normal vector would be 0, 1, 0. So we're pointing here in the positive y direction. Okay, so what we can say is now by Stokes theorem, we can do the following. The integral along the curve of f dot dr is equal to our integral over our surface, we'll call our surface G, just need a name, of the curl of f dot n, which is 0, 1, 0. dSA. So now we need to do the curl of f. So we're going to do the curl of f. We'll come down here. Curl of f. Well, I, j, k, partial x, partial y, partial z, and we have our various expressions. Now, looking at this, we know that not all expressions are equally important, and some are more important than others. Now, which one is important? The second entry. The second entry matters. The first and the third entry won't matter because we're going to be multiplying them by 0. So this is going to be equal to stuff. And on the test, you're going to have lots of time, so you can fill in what the stuff is. But we're a little short. I want to make sure we get through all the problems. So something, and then in J, well, what do we have? We're going to have partial z of 5 plus z times log of 1 plus y squared. So that'll be 5 plus log of 1 plus y squared. That makes us a little bit nervous. That's what we get from going in one direction. But remember, it's going to get worse because we're also going to subtract what? Partial x of the derivative of this. So taking the derivative of this with respect to x is 1 plus log of 1 plus y squared. Now we have even twice as many of log of 1 plus y squared to worry about. Or do we? The answer is we don't. Because what happens? They cancel. So the curl of f becomes something fairly reasonable. It's something for something. So, coming up here, this becomes the integral over our surface of something for something dot 0, 1, 0 dSA. And so that's a 4 when you multiply it out. So this is 4 integral of the surface of the area. D surface area. So that's 4 times whatever the area of our surface is. Well, let's look at our surface. It's a square. It's a square which has sides of length 2. And I know it has sides of length 2. It says it right there. So how much area is there? Well, 2 by 2 square has area 4, giving us our final answer of 16. Sure. Yes? Oh, yeah, the 5 would be 0. Making this negative 1, making this negative 1, making this negative 1, making this negative 4. My negative 4 looks really a lot like 16, so, okay. Thank you. Yeah. Double check your work. What a great life lesson. Check your work. Check your work. Thank you. All right. Look, you'll never outgrow small mistakes, which is why you always say, wait, shouldn't it be this? No, yeah, maybe it should. All right. Find all the lines which are tangent to the parametric curve. R of t is t cubed minus 12t plus 3, and t squared plus t minus 4, and 2t squared plus 5t plus 4, which do not intersect the plane 2x plus 3y minus 3z equals pi. So I don't want to hit that plane. I want to avoid that plane at all costs. So we're looking for lines which do that. So we have to think about what's true. So I have this line sitting here, and I say to myself, well, when will a line not be in the plane? In other words, not be in the plane, but miss the plane. So if I have a line up here that's not in the plane, there's something that has to be true. Namely, I could actually cast a shadow and would actually end up being in the plane. So what does that say? Well, they're parallel to each other. And so the direction of the line that doesn't hit a plane has to be a direction of a line in the plane. All right, well, what does that mean? In particular, what this says here is if we think about our normal vector to the plane, it's got to be perpendicular to that shadow, which means that the normal vector to our plane has to be perpendicular to our line. So if a line and a plane don't intersect, the normal vector to the plane has to be perpendicular to the direction of the line. So we have an idea. What do we need? Well, we need that this vector here, 2, 3, negative 3, has to be perpendicular to our direction of our tangent line. So what do? Well, we're going to take our tangent line and let's figure out what our direction would be and just make sure we find something where it's going to be perpendicular. Now, if I want direction for a tangent line to a curve, that says I should be looking at the motion. Motion tells me direction. So I come here and I compute r prime. So what is that? 3t squared minus 12, and the 3 goes away. 2t plus 1, the minus 4 goes away, and 4t plus 5. All right, so that's my tangent line, or rather, excuse me, that's our velocity, is often how we think about it. But that gives us our direction for any given value of t. And now what we need is to say, well, we want to make sure our direction is perpendicular. So how do we know if two things are perpendicular? What's the test? Dot product. So we need to make sure 3t squared minus 12 and 2t plus 1, comma, 4t plus 5, that's a really big comma, dot 2, 3, negative 3 is 0. So let's see where that takes us. So multiplying these together, we'll get 6t squared minus 24, that's the first two, plus 6t plus 3, that's the second, and plus minus 12t minus 15 has to equal 0. Well, let's see. So that's 6t squared. There's a 6t minus 12t, that's minus 6t. Then we have minus 24 plus 3 makes minus 21. Minus 15 more makes minus 36 equals 0. So that has to be true. So we now need to find all the t that do that. Now that's looking pretty promising. It looks like a polynomial. In fact, everything's divisible by 6. T squared minus t minus 6 equals 0. And now we say, okay, factoring has been our friend this whole semester. Just a few days more. Just a few days more is all we need factoring. And does it factor? It does. T minus 3 times t plus 2 equals 0. Okay, good. So what's that tell us? Well, it tells us that our tangent lines are going to not hit when we look at the tangent lines at time 3 and negative 2. So there's 2 times when our tangent line to our curve is going to miss the plane. All right. Well, are we done? The answer is no, because we weren't asked to find the time. We were asked to find the lines. So if we're going to find the lines, our answer had better be lines. All right. So now, what do we need? Well, we know when it happens. Now we just need to find what happens. So we need to know what is r of 3. And so r of 3, we go through, do the math, 27 minus 36 plus 3. Well, probably 27 plus 3 is easy. That's 30. And then subtract 36 is negative 6. Here we'll get 9 plus 3, which is 12. Subtract 4 gives 8. And then we're going to have 9 times 2 is 18. Plus 15 is 33. Plus 4 more makes 37. So there's r of 3. What about r prime of 3? Well, we have that too. We can just plug it in here. So we're going to get 9 times 3 is 27. Minus 12 is 15. Then we're going to get 6 plus 1 is 7. And then we're going to have 12 plus 5 is 17. So there's our 15, 7, 17. We also need to do the same thing for negative 2. So r of negative 2. So we're going to get minus 8 plus 24. which is 16, plus 3 makes 19, and negative 2, so negative 2 squared is 4. Subtract 4 is 0, and then plus 2, plus negative 2. Here we're going to get 8, because we'll get 2 times 4. Plus 4 more makes 12. Subtract 10 gives 2. So that's r of negative 2, and r prime of negative 2. So that's 12 minus 12, which is 0. Oh, that's nice. Minus 4 plus 1, which is minus 3. And minus 8 plus 5, which is also minus 3. And once you have this, now we get our two lines. So, well, we did parametric last time. We'll do vectored value this time. So we can say our first line is x, y, z is equal to our point, minus 6, 8, 37, plus t times the direction, 15, 7, 17. And the other line, x, y, z, equals 19, negative 2, 2, plus t times 0, negative 3, negative 3. And those are our two lines. All right, so a lot of this problem, I will say if you see problems like this, and it may or may not, because there's lots of things that we're going to see. Not everything has to show up. But if you see something like this, think about the geometry. What has to be true? You know, what things are parallel? What things are multiples of each other? Which things are perpendicular? And don't overthink it. Don't overthink it. Of course, don't underthink it. The right thing to do is to think. If you think, that's going to get you a long ways. So, let G be the surface. Z equals x plus y squared over the region R. And what's R? X goes between 0 and 1, and y goes between 0 and e to the x squared. That's a bold region. N is the upward polynomials to the surface, and what are we going to ask to find the integral of g of 3x minus zi plus y times j plus z times k dot n dsa. Now, we might think to ourselves, okay, what problem is this? So, let's think. Is this a divergence theorem problem? And the answer is no, because this isn't a solid. Our surface G is not the bounding surface of a solid. This is not divergence theorem. Say, good. So it's Stokes theorem then. No. Why is it not Stokes theorem? There's no curl. This isn't the curl of something. If it was the curl of something, that's Stokes theorem. You might say, well, maybe this is the curl. We just have to find what it came from. The answer is no, this is not the curl of some other function. You can actually check that. So it's not divergence theorem, and it's not Stokes theorem. And at that point, you're thinking, well, what is it then? And the answer is, it's a flux problem. Flux through a surface. So what do we have? If you have z equals f of x, y with upward normals, and we do, that's the good news. And then what you have is that the integral along G, I should say this is over region R, then the integral of G of mnp dot n is equal to the integral over your region of minus m fx minus n fy plus p dA. So this is just one of those problems where it's like, all right, we don't have our powerful tools, but even though we don't have our powerful tools, we still have tools. And so we apply our tools. So this is just a straightforward, we hope, do the problem. Now remember, one of the things that you have to make sure is no z's. Now how do you get rid of the z's? Use your function, z equals f of x, y. You can replace any z's that are left with your function. So that's our tool. So we're going to have the integral over our region of minus 3x minus z. So I'm going to replace z by x plus y squared. So that's minus m times f sub x. in this case it's 1, plus, whoops, not plus yet, still minus, so I'm up to that minus n, so here n is y, times f sub y, so that's times 2y, plus p. In our case, p is z, but again, we don't want any z's, so we replace that by x plus y squared. All right, so that's what we have to find. Well, what do we have? Let's clean this up. From the first term, we have 3x minus x. That looks like, I guess, a 2x, if I'm doing that right. Yeah, that's 2x. Then you have minus minus makes plus y squared. The middle term, minus 2y squared. And then here on the end you have plus x. And then finally plus y squared dA. Well, does anything nice happen? You got a lot of y squareds, but the good news is if you look at it, you got plus y squared, and minus 2y squared. They all cancel out. So this simply becomes, well, if simple is the right word, integral of 3x. Well, what's our region? Well, it actually gives it in a nice way. 0 to 1, 0 e to the x squared, 3x dy dx, where x goes from 0 to 1, y goes 0 to e to the x squared. So where does this become? This becomes integral of 0 to 1, 3xy from y equals 0 to y equals e to the x squared dx, which becomes the integral of 0 to 1 of 3x e to the x squared. Ah, well that's good. That's good. Now why do I say that's good? Well, e to the x squared you can't integrate, but with that x out in front, it helps. In fact, what? Where? Ooh, you're right. I am so sorry. There should be, yes, negative 2x, which makes this negative x. Thank you for correcting me. Makes that negative x. But still, the x is helpful. Even though the number changed, the part that helps us didn't. So the integral of x e to the x squared turns out to be 1/2 e to the x squared. It's an easy substitution to make. Evaluate that from 0 to 1. And so you get minus 1/2 e and minus 1. All right. Good. Now, you might, for a second, say, we got a negative number. Is that okay? Is it okay to have negative flow? And the answer is, yeah, it's okay to have negative flow. So that's all right. Okay. Find the integral from 0 to 1, the integral from arctangent of y to pi to the fourth, cosine log of secant of x dx to y. You knew that we'd have to end with an arctangent. This is the last chance we're all going to be together. So we've got to end on a positive note. So what does this look like? Well, we have a couple of things. We have this surface x equals arctangent of y. Now, if you plot arctangent, you just turn it on its side. So it looks something like that. And let's see, what do we have? We also have x equals pi fourths. That looks something like that. And it turns out, here's 1. And so this is our region. We're going, y goes from 0 to 1, go to arctangent of y up to pi fourths. Okay. Now, looking at this, the integral of cosine of log of secant of x dx does not look like a pleasant integral to do. And so the trick is, we don't do it. We say, look, I don't want to integrate with respect to x. I'd much rather prefer to integrate with respect to y. All right, we can do that. We'll just switch our order of integration. So it's still the same function on the inside, cosine log secant of x, but we're going to switch our order to dy dx. But if we do that, we've got to figure out our bounds. So let's see, where does x go from? Well, 0 up to pi over 4. And where does y go from? Well, we're now going to go up. So we're going to start at 0 and go up till we hit this curve. Now the curve was x equals arctangent of y, but it could also be written as y equals tangent of x, because that's the inverse of the arctangent. So 0 up to tangent of x. So that's 0 to pi fourths, and cosine log secant x times y, evaluate y equals 0 to y equals tangent of x. And if we evaluate, we'll get cosine log secant of x times tangent of x. Notice 0 gets 0. And we say, well, is that any better? Well, we think to ourselves, can we do this? We suspect something should happen. Let's try setting the inside part here, u equals log secant x. What's du become? What's the derivative of log of secant of x? It's tangent of x. Almost as if they wanted something nice to happen, because they wanted something nice to happen. So there's our du. So this becomes the integral of cosine of u du. Plug in your bounds, because you have to update your bounds. Remember, these are x bounds, and we want to go to u bounds. So at x equals 0, secant of 0 is 1. So log of 1 is 0. At pi fourths, secant of pi fourths, do you remember? Square root of 2. So log of square root of 2. Integral of cosine is sine. And then we're going to evaluate from 0 to natural log of square root of 2, giving us, since sine of 0 is 0, we'll end up with sine of natural log of square root of 2. Just like you would have thought when you started the problem. All right, and that's it. We hope you do well on the exams, and if you can do the problems we talked about today, you will. You know, these are the types of problems that you might see.